We're all navigators. We have to be, because we spend so much of our lives moving from place to place, usually with some particular objective in mind, and with particular hazards to avoid. In less familiar surroundings, we might have to ask directions. Alternatively, we could consult a map. A map, in a way, is like a set of universal directions. So long as you can understand its language, it can tell you the way from anywhere to anywhere. Navigation at sea is much the same. There are objectives to meet, and hazards to avoid. One big difference is that we're not confined to particular roads or tracks, so we can't rely on signposts or directions. Everyday navigation at sea depends very much more on maps, except that marine navigators call them charts. Road atlases and street maps usually use a grid system to help relate the names of the places in the index with their actual position on the map. Marine charts use a similar system, except that ours is international and covers the whole world. It's called latitude and longitude. The latitude of a place tells us how far north or south it is, referred to the equator. Falmouth, for instance, is just over 50 degrees north of the equator. Longitude tells us how far east or west it is, compared with an imaginary line called the prime meridian, which passes through Greenwich. Falmouth is about 5 degrees west of Greenwich. Latitude and longitude are both measured in degrees, corresponding to angles measured at the centre of the Earth. In fact, this is a bit of an oversimplification, but it'll do for the moment. More important is that a degree is quite a large unit of measurement on something as big as the Earth. For practical purposes, each degree is divided into 60 minutes, and the minutes are then subdivided into tenths, hundredths, and sometimes even thousandths. Black Rock Beacon, for instance, is at 50 degrees 08.68 north and 5 degrees 01.94 west. On land, our freedom to manoeuvre is usually limited. We're constrained to a narrow strip of road and can only turn left or right at road junctions. At sea, we have infinitely more choice, so we need a more sophisticated system for measuring and naming directions. In days gone by, different directions were given names: north, south, east and west. These names are still used for approximate directions even on land, but at sea they are now almost obsolete. We now specify direction as an angle measured in degrees and counting clockwise from north. Distance, of course, is very nearly as important. At sea, it's almost invariably measured in nautical miles or sea miles. Strictly speaking, there are subtle differences between the two, but for most practical purposes, you can assume them to be the same, and that both are equal to 1 minute of latitude, or 1,852 metres. Charts are marine maps. Like land maps, they're available at a wide range of different scales. Small-scale charts cover large areas, but don't show much detail. At the other extreme, very large-scale charts may show just part of a single harbour. Regardless of their scale, all charts are drawn on a grid of parallels of latitude and meridians of longitude. On most charts, the meridians and parallels cross each other at perfect right angles. Of course, this can't be a perfectly accurate representation of the real world, where the meridians curve to meet each other at the poles and the parallels are really circles. Representing the curved surface of the Earth on a flat sheet of paper inevitably involves some kind of distortion. Marine navigators are usually most concerned about direction, so charts are designed to represent directions accurately, at the expense of small distortions in distances. Onto this framework of latitude and longitude, cartographers superimpose important information. Top priority, of course, has to be the coastline. On a British Admiralty chart, areas which are above the high water mark are shown yellow. Those which cover and uncover with the tide are coloured green and are bounded by this line, called the drying line. Contour lines, just like those used on land maps, are used to show the shape of hills. Other contours reveal the hidden geography of the seabed. All over the chart you'll find other symbols, mostly relating to important landmarks or sea marks. There are so many different symbols that it's difficult to remember them all. Admiralty small craft chart folios include a key to the most important symbols. But the ultimate reference is this booklet, called Chart 5011. Direction is so important to navigators that we use lots of different words to refer to it, and have several different instruments to measure it. The traditional swinging card compass uses magnets to keep the graduated compass card lined up with the Earth's magnetic field. It gives us, quite literally, a sense of direction. There are alternatives, however. Electronic compasses, called fluxgates, are becoming much more popular, especially as a fluxgate heading sensor can be used to control an autopilot and can pass information to a radar or chart plotter. One important use for a compass is to tell us which direction the boat is heading in. That's the job of a steering compass, whether it's a fluxgate or a swinging card. Often, however, we want to know the direction of something else from us. That's called its bearing. So the tool we use to measure it is called a hand-bearing compass. One big snag with any kind of magnetic compass is that the Earth's magnetic field isn't perfectly lined up with its axis of spin. This means that a magnetic compass doesn't point to the true North Pole, but to the magnetic pole, amongst the islands off northern Canada. The compass, in other words, is subject to an error. It's called variation because it varies from place to place and from time to time. Variation, however, is always shown on navigational charts. Here, for instance, it was 2 degrees 55 minutes west in 2001, and it's moving eastward at 8 minutes per year. Knowing the compass error, we can allow for it by arithmetic. Suppose we can see a lighthouse on a bearing of 230 degrees by magnetic compass. The variation from the chart is about 5 degrees west. Generations of sailors have used a simple rule called the cadet rule to tell them whether to add or subtract variation. When going from compass to true, the rule says we must add easterly variation. We're converting from compass to true, but the variation is west, so we've got to subtract it. The other snag with a magnetic compass is that it is easily influenced by magnetic objects on board. Of course, you should take care not to let magnetic objects get too close to your compass. But there are always going to be some things that you can't do anything about. Engines, keels, electrical systems, radios and instruments all set up magnetic fields that are peculiar to each particular boat. The effect of this on the compass is called deviation. A skilled compass adjuster can fit special magnets to counteract deviation. As well as this, however, he'll produce a deviation card showing the remaining deviation. Allowing for deviation is just like allowing for variation, except that it changes with the direction the boat is pointing in. Suppose we're steering 075 by compass. On this heading, the deviation is 3 degrees east. We're going to use the cadet rule again. In this case, we're converting from compass towards true, so we need to add easterly errors. That shows that 075 compass, in this case, is 078 magnetic. We can then convert this from magnetic to true. A single direction, then, can be known by several different names. In this case, 075 on the compass corresponds to 078 magnetic, and to 073 degrees true. We've just seen how compasses of various types can be used to measure direction on the real world. Somehow, though, we have to be able to relate that to the chart. The grid of meridians and parallels give us the 4 cardinal directions: north, south, east and west. But for all the in-between directions, there are these compass roses, and a variety of different plotting instruments. A plotter like this has a rectangular base and a rotating circular protractor. If you want to measure a direction, such as between these two buoys, you just line up the base and turn the protractor until the square grid is lined up with the parallels and meridians on the chart. Then you can read off the direction from the scale, here. If you want to draw a line in a particular direction, the process is reversed. Set the direction you want on the scale, put the plotter on the chart with its grid lined up with the parallels and meridians, and slide it around as necessary until one edge passes through the point you want to start drawing from. Parallel rulers are a more traditional tool for the same job. To measure the direction between these two buoys, start by lining up the ruler just as we did with the plotter. Now we have 2 choices. We could open the rulers until the tip of the S mark just touches one of the vertical meridians. Then, keeping that ruler still, close the other one up to it, and read off the direction where the meridian cuts the scale engraved on the edge of the ruler, here. The alternative is to walk the rulers across the chart to a compass rose. Drawing a line in a particular direction is again the reverse. This time we're going to use a rolling parallel rule. We can either roll it across from the nearest compass rose, or can line up the S mark and the required number on a meridian, and then adjust its position a little if necessary. The other measurement that is absolutely fundamental to navigation is distance, and in particular the distance we've travelled through the water. Here's a fairly primitive but effective instrument for measuring it. The body of the instrument contains a gearbox linked to several dials. Hooked onto the back is a long length of line, and on the end of that is a spinner. As the boat tows the spinner through the water, it twists the string which turns the gearbox and moves the hands on the dials to show the distance the boat has travelled. More modern versions use a smaller spinner or paddle wheel mounted through the hull of the boat. As the water flows past the hull, it spins the paddle wheel. Little magnets built into the paddle wheel create electrical pulses which travel up to the instrument display head. Up here, the display unit counts the pulses and displays the boat's speed and the distance it has travelled. As with direction, it's one thing to measure distance in the real world, but we somehow need to relate that to the chart. Remember that a sea mile and a nautical mile are effectively the same thing, and that a sea mile is the length of 1 minute of latitude. The standard tool for the job is a pair of dividers like these. The shape isn't just a matter of tradition. It means that the dividers can be opened or closed with one hand. So to measure the distance between these buoys is a simple matter of opening the dividers and transferring that distance to the latitude scale. 12.5 miles. There's one other instrument that is pretty well standard on all cruising boats. That's an echo sounder for measuring depth. Until about 40 years ago, the only way most small boat navigators could measure depth was by poking the bottom with a pole or by dropping a lead weight on a string. Echo sounders were the first electronic instrument to become popular. They work by producing barely audible clicks of high-pitched sound. Each click travels downward to the seabed and is reflected back as an echo. Sound in seawater travels at an almost constant speed of about 1,500 metres per second. So if it takes 1/100th of a second between the click being transmitted and the echo being received, the sound must have travelled 15 metres. So the seabed must be 7.5 metres from the transducer. In practice, this information can be presented in several different ways. Most early echo sounders showed the depth as a blob of light against a circular scale. Nowadays, digital displays are very much more common. But some people prefer a graphical presentation, such as on this fish finder. Whatever kind of echo sounder you use, it's important to appreciate that the depth it shows may not correspond with the depth shown on the chart. Part of the reason for this is that the echo sounder measures the depth from the transducer. In most cases, it's a simple job to calibrate it to show either the depth below the keel or the depth below the waterline. The other part of the reason is that sea level rises and falls with the tide, so in most cases you should find that the echo sounder shows rather more water than it shows on the chart. Being able to measure the direction we've moved and the distance we've covered gives us a fairly obvious way of working out where we are. If we know that we started here, and that we have travelled in this direction for a distance of 5.25 miles, common sense says that we must be here. This method of navigating, based only on the course steered and the distance travelled, is known as dead reckoning, or DR. It's the basis of a lot of other navigation techniques. By itself, though, it's not very accurate. You can see that we're quite a long way from where the dead reckoning plot says we should be. One possible explanation is that the water itself is moving and carrying us with it. From childhood holidays, most of us know that sea level rises and falls. All this extra water must have come from somewhere. Tides are an astronomical phenomenon, so they're as predictable as sunrise and sunset. The sun does have a part to play, but it's the moon that is the dominant factor. The moon and Earth whirl through space as a lopsided pair, held together by the invisible bonds of each other's gravity, and rotating about a point just a few hundred miles below the Earth's surface. While the Earth's gravity holds the moon in its orbit around the barycenter, the moon's gravity is doing the same for the Earth. The water nearest the moon, however, is a bit closer to the moon than the Earth itself is, so it's attracted towards the moon more strongly. Meanwhile, the water furthest from the moon is attracted less strongly, so it tries to fly off into space. It's held back by the Earth's own gravity, but still bulges outwards. These two bulges, tidal waves in the truest sense of the word, travel round the Earth once a month in step with the moon. Of course, while all this is going on, the Earth itself is spinning. Someone standing or floating on the surface of the Earth sees one high tide roughly once every 12.5 hours. High tides aren't all equal. For one thing, the moon's orbit isn't perfectly lined up with the Earth's axis of spin. So although the two tidal bulges are about the same size, they're lopsided. Someone on the surface of the Earth will see a big tide, followed by a small one, followed by a big one, and so on. While the moon is doing its stuff, the sun is also having an effect. It produces tides in much the same way as the moon, but only about half the size. Roughly once a month, at the time of new moon, the sun's tides add to those produced by the moon to produce higher high waters and lower low waters than usual. About a week later, the geometry has changed. Now the sun's tides are detracting from the moon's tides, producing smaller tides than usual. A week later, at full moon, the sun is reinforcing the moon's tides again. The small tides are called neaps, and the big ones are springs. In practice, all sorts of other factors conspire to make the real tides far more complicated than this, but they can still be predicted. Tide tables like these are published in almanacs, in separate books, and even as computer programs. They show the time and height of high and low water for every day of the year. Times are pretty obvious, though you may have to check which time zone is in use. Here, for instance, we need to add an hour to the published time to allow for British summertime. Alongside the times are the corresponding heights. It's pretty obvious that 1.2 metres is low water and 4.4 metres is high water. But where are they measured from? The answer is that they're measured from an arbitrary level which roughly corresponds to the lowest level the tide is ever expected to reach. It's called chart datum. Low water at a typical spring tide may be only a few centimetres higher than this. High water springs, however, may be several metres above it. The difference between these two varies from place to place. In the Bristol Channel, for instance, it can be as much as 12 metres, while in parts of the Shetlands, it's barely a metre. Neap tides have higher low waters and lower high waters, so their range is smaller, usually about half that of a spring tide. The depths shown on charts are invariably measured from chart datum. So too are the heights of things such as rocks and sandbanks which cover and uncover. Heights of things such as islands, lighthouses and bridges, however, are measured from high water springs. We've seen that tide tables show the times and heights of high and low water at major ports on every day of the year. Here, for instance, we can see that low water was at 0050 and was 1.1 metres above chart datum, and that high water will be 5.3 metres above chart datum at 0625. That may be very useful if we happen to be in the area at those times, but what about now? The tide doesn't rise and fall at a constant rate. From low water it rises slowly at first and then more quickly, before slowing down as it gets towards high water. Then it goes through a similar slow, quick, slow routine as it falls. As a rough approximation, you can say it takes 2 hours to rise by the first quarter of its range. Then it rises by half its range in the next 2 hours, and takes another 2 hours to rise the last quarter of its range. In this particular case, low water was 1.1 metres about 2 hours ago. High water will be 5.3 metres, so the range is 4.2 metres. In the 2 hours since low water, the tide will have risen about a quarter of that range, so water level is now about 2 metres above chart datum. If you want to be more precise, there's another rule of thumb called the rule of twelfths. It works in much the same way, but uses 1 hour intervals. In the first hour, the tide rises or falls by 1/12 of its range. In the second hour, it rises or falls by 2/12. And in the third hour, it rises or falls by 3/12. Then it starts slowing down again from 3/12 in the fourth hour to 2/12 in the fifth hour and 1/12 in the final hour. The rule of twelfths works quite well for harbours like Falmouth, whose entrances lead straight into deep open water. Places like Portsmouth, with shallow approaches and nearby islands, are very different. Here, the shape of the tidal wave is distorted as it runs into shallow water and is funneled through different channels. To cope with this, most tide tables include graphs showing how the tide rises and falls. Here is the time scale referred to the time of high water. And here is the height scale, showing the height above low water as a proportion of the range. Attached to the graph there's a ready reckoner. Suppose, for instance, we want to know when the tide at Portsmouth will reach a height of 2 metres above chart datum. The tide tables show that low water today is 0.9 metres and high water is 4.4 metres. So we mark them on their respective scales and join the two marks with a straight line. From the height we're interested in, 2 metres, drop a vertical line down to meet the sloping line we've just drawn. From there, draw a horizontal line across to meet the graph. Use the dotted graph if it's a neap tide and the solid graph if it's a spring. Finally, drop a vertical line down to the time scale to read off the time. Of course, if we want to know the height of tide at a particular time, we can do the same thing backwards. Prepare the ready reckoner by marking up the heights of high and low water just as before. This time, though, we're going to start from the time we're interested in and rule a line upwards to the curve. From there, we move across to the ready reckoner and then up from the diagonal line to read off the height. A lot of research and investment goes into producing tide tables for major ports, but as small boat navigators we're often interested in smaller harbours, for which full tide tables simply don't exist. Almanacs and tide tables do, however, include information like this. It can be presented in several different ways, but basically it's telling us the difference between the harbour we're interested in and the nearest one for which full tables are available. Suppose, for instance, we want to know what the tide is doing at Woodham on the 14th of November. The difference table tells us that it's referred to the standard port of Sheerness, so the first job is to look up the data for Sheerness. Back on the differences table, the information is presented in several columns. The first 4 relate to times, and the other 4 to heights. Of the 4 time columns, the first 2 relate to high water and the other 2 to low water. And of the 2 high water columns, the first one tells us the differences when high water is at 2 o'clock in the morning or 2 o'clock in the afternoon, while the other tells us about high waters that happen at 8 in the morning or evening. In this case, you can see that if high water Sheerness is at 1400, then high water at Woodham would be 30 minutes later at 1430. If low water Sheerness is at 1900, then low water Woodham is going to be 1 hour 20 minutes later. Notice that 0120 means an hour and 20 minutes, not 120 minutes. On this particular day, low water at Sheerness is at 0524. You could say that 0524 is roughly 2/3 of the way between 0200 and 0700. So the difference must be roughly 2/3 of the way between 35 minutes and 1 hour 20 minutes, so roughly 65 minutes later. Exactly the same process applies to the time of high water. The calculations for heights are very similar too. Here, high water is 5.2 metres. The difference table says that if it had been 5.8 metres, the difference would have been minus 0.2 metres, and that if it had been 4.7 metres, the difference would have been minus 0.3 metres. Let's take the difference to be minus 0.25 metres. Again, the low water calculation is just the same, using the low water data. And at the end of it all, we've produced a complete set of tidal information for Woodham. If you have the need for this level of accuracy on a regular basis, then it might be worth investing in one of the many computer programs that will do all the calculations for you and even print out monthly predictions. The only reason any of this is necessary is that sea level is constantly rising and falling at different rates and times in different areas. Huge quantities of water, in other words, are constantly on the move. Drifting boats inevitably go with the flow, while moving ones can be speeded up, slowed down, or pushed sideways by it. These tidal streams can even affect the sea state, producing rough patches where they flow over shallow areas, round headlands, or against the wind. The relationship between tidal streams and tidal heights isn't straightforward, but they're definitely related. So tidal atlases like this can show the changing tidal streams at every stage of the tidal cycle. Each chart relates to a particular time, referred to high water at a standard port. This one, for instance, shows what the tidal streams are doing in the Western Approaches and English Channel at high water Dover, while this one shows the slightly different situation an hour later. A lot of navigators find it useful to mark the corresponding clock time onto each page. Arrows show the direction of the tidal stream at different places. Here, for instance, it's flowing eastwards. The numbers refer to the speed of the flow at neaps and at springs. They are given in tenths of a knot, so 0815 means that there is 0.8 knots of tide at neaps and 1.5 knots at springs. Standard navigational charts include the same information, though it's not in quite such user-friendly form. The table is made up of several boxes, each dealing with the tidal stream at one particular place. It's identified by a letter marked on the chart. For each hour before and after high water at a standard port, it shows the direction of the tidal stream and its spring and neap rates. Now let's see how this information can be used to improve on dead reckoning navigation. You'll remember that dead reckoning, or DR, is based only on where we started from, the direction we've been steering, and the distance we've travelled. First, we might want to allow for the fact that a boat doesn't always move through the water in quite the direction that she's pointing. Even in perfectly still water, the wind tends to push all boats sideways to some extent. It's called leeway. And if you can make a realistic estimate of it, then it's worth applying a correction to the boat's course before you plot it on the chart. The next step is to allow for the distance we've travelled through the water. This is a DR position, but allowing for leeway. For the past hour, however, the tidal stream means we've been on a moving carpet of water. The tidal stream atlas in our almanac shows that it's been moving southwestwards at 2.3 knots, so in an hour it will have pushed us 2.3 miles to the southwest. The end result is called an estimated position, or an EP, and is traditionally marked with a triangle and the time. In that case, the estimated position was based on exactly 1 hour's run, but it doesn't have to be. We could do it over a part hour, or as is happening here, over several hours. You can see that this DR position is based on 3 hours run, including a couple of minor course changes. That doesn't matter, as long as we allow as many hours' worth of tide as of distance run. Here's the first hour. Here's the second, following on from the first. And here's the third, giving an EP here. Suppose we wanted to row across a river. It's one thing to set off in roughly the right direction and work out where we are as the tide pushes us around. It would be much better, though, to allow for the tide in advance. The principle is simple. The current would sweep us downstream, so the direction we're actually moving, called our ground track, is quite different from the way the boat is pointing, called its course or heading. To row straight across the river, we need to aim upstream to counter the effect of the current. In real life, over short distances, we might do this by keeping two objects lined up with each other. Over longer distances, we need to work it out on the chart. Suppose we want to go from Penlee Point to the Eddystone Rocks. The distance is about 8.5 miles, so we estimate it should take about an hour. From the tidal stream information on the chart, we can see that the tide will be setting us eastward at 0.8 of a knot. Now we've got two sides of the vector triangle we saw a few moments ago. The third side is decided by our speed. We're expecting to make 8.5 knots, so in 1 hour we should do 8.5 miles through the water. With the compasses or dividers set to 8.5 miles and the point at the end of the tidal stream vector, make an arc across the line that represents our intended track. This line, from the end of the tide vector to the point at which the arc cuts our intended track, represents the course to steer. It doesn't matter if the corner of the vector triangle that we've just drawn doesn't fall exactly on our intended destination. It very rarely does. If it's a long way short, however, it means the trip is likely to take a lot more than an hour, so we need to look at more than an hour's worth of tide. On a longer trip, start with the intended track from departure port to destination and work out a rough estimate of how long it should take. Look up the tidal streams that you're likely to experience along the way, and mark off these tidal vectors from your starting point. We've allowed for 6 hours' worth of tide, and we're expecting to make 14 knots, so we should cover 84 miles through the water. With the compasses or dividers set to 84 miles, and the point at the end of the last tidal stream vector, make an arc across the line that represents our intended track. This line, from the end of the tide vector to the point at which the arc cuts our intended track, represents the course to steer, just as it did when we allowed for just 1 hour's worth of tide. Working out a course to steer by this traditional method can be quite time-consuming. Sometimes it's hardly worth doing, or else it's just too difficult. An alternative is called the 1 in 60 rule. It's based on the fact that a triangle 60 miles long and 1 mile wide will have an angle of almost exactly 1 degree. A triangle 60 miles long and 10 miles wide will have an angle of almost exactly 10 degrees. So let's suppose we're setting out on a 60-mile passage at 20 knots. For the first hour, there will be a 2-knot westbound tide. For the second hour, it will increase to 4 knots, before dropping away to 2 knots again for the third hour. All told, the tide will push us westwards about 8 miles. Using the 1 in 60 rule, we can tell immediately that 8 miles off track on a 60-mile passage needs an 8-degree correction. Of course, the same principle applies to longer or shorter passages. You just have to do a bit more mental arithmetic. From Land's End to the Scillies, for instance, is about 40 miles. If the tide is likely to push us 3 miles south in the time it takes us to cover 40 miles, then it might push us 4.5 miles south in the time it takes us to go 60. In other words, we need to steer about 4.5 degrees further north to compensate for it. Until relatively recently, navigation at sea was very much concerned with working out where you were. There were, and still are, plenty of ways of doing it, but checking the DR and EP could sometimes become almost a full-time job. In the early 90s, finding your position began to change, with the introduction of a new electronic navigation system. The Global Positioning System, GPS, revolutionised navigation as much as the invention of the compass had done many centuries before. It uses a constellation of about 24 satellites, orbiting the Earth at an altitude of about 11,000 miles. Each satellite continually broadcasts a coded signal, saying in effect that I am here and the time is now. A compact and relatively economical receiver on board picks up the satellite broadcast and compares the time at which it was sent with the time at which it was received. Knowing how long the signal has taken to cover the distance from the satellite to the receiver, and knowing that radio waves travel at 300 million metres per second, the receiver can work out how far it is from the satellite. Once the receiver knows that it is, say, 24 million metres from the satellite, it knows it must be somewhere on the surface of a huge sphere with a radius of 24 million metres. At the same time, it can be doing the same calculation for several other satellites, producing several other position spheres. In principle, all those position spheres should intersect at a single point, which must be where the receiver is. In practice, errors in the receiver's clock mean that the spheres seldom intersect as neatly as this, but if they don't, the receiver is able to adjust its clock until they do. The end result is that the receiver knows where it is, usually to an accuracy of about 15 metres or so. Using a GPS is very simple, but you should still read the manual first. In any case, when it is switched on for the first time, it will usually take a few minutes to find out where it is. You can usually speed up the process by giving it a rough idea of where it is and what the time is. You may want to customize your GPS too, setting it up to give information in the right units, such as nautical miles and knots. One particularly important setting is concerned with the horizontal datum. At the beginning of this programme, we said that latitude and longitude are measured in degrees from the centre of the Earth. The trouble is that the Earth isn't a perfect sphere, so its centre appears to move slightly depending on where you are. The effect of this was that in the years before satellite navigation systems, charts of different parts of the world were drawn using slightly different grids of latitude and longitude. The discrepancies can be as much as several miles, but they aren't usually that big. Around Britain, for instance, the difference between the British datum and the newer worldwide datum used by GPS is less than 200 metres. It's still a lot bigger than the position errors of 15 metres or so of the GPS system, and as all GPS sets can convert from one datum to another, it's worth making sure the datum set on your GPS is the same as the datum of your chart. Almost as a byproduct of all this, a GPS set can also work out various other pieces of navigational information, such as your speed and direction of movement and the time. It's important to appreciate, though, that a GPS set is not a log or compass. It shows the speed you are moving over the ground, not through the water, and the direction you are moving, known technically as your track, rather than the direction you are pointing. Another powerful feature of most GPS sets and all plotters is known as waypoint navigation. This lets you specify particular positions known as waypoints that you want to go to. Here, for instance, we're intending to sail from Lymington to Cowes. We can key in the latitude and longitude of our waypoints, or as we're doing here, entering them using the cursor. Remember to check that you're in safe water at all times. The GPS or plotter cannot distinguish between land and sea and will guide you over a buoy or rock if it happens to be on your track. Once we've told the GPS where we want to go to, it can tell us the direction we need to travel to get there, the bearing to waypoint, the distance we have to go, and how far we have strayed off the straight line track between the two waypoints, known as our cross-track error. All this information can also be used by an autopilot to keep the vessel on track automatically. GPS may have revolutionised navigation, but the old ways still work, and there are times when they're actually easier or more useful. The easiest fix of all is obtained just by passing close to a charted object. We can then mark our position on the chart using the circle that is the conventional symbol for a fix and label it with the time. A hand-bearing compass lets us get a fix without having to find such a convenient mark. The principle is quite simple. Here, for instance, the hand-bearing compass shows that the chimney is on a bearing of 032 degrees from us. Remembering that any magnetic compass is subject to variation, we need to convert that bearing to true, using the cadet rule that we mentioned earlier in the programme. Having done that, we can then draw the line on the chart, passing through the chimney to represent our line of sight. Our position must be somewhere on that line. If we do the same with another landmark, we'll get another position line. The only place we can possibly be on both position lines at once is where they cross. In practice, it's always better to take 3 bearings and plot 3 position lines. You'd expect all 3 to cross at the same point, but in practice they very rarely do. Instead, they form a triangle, traditionally called a cocked hat. Each position line is serving as a check on the accuracy of the other 2, so as long as the cocked hat is reasonably small, we can still regard it as a fix. A large, straggly cocked hat, on the other hand, is a warning that something isn't quite right, and that the bearings need to be taken again. There are a handful of simple rules which will help keep the cocked hat small and reliable. 1 is to make sure that you have identified the landmarks correctly. 2 is to choose landmarks that are well spread, not close together or 180 degrees apart. 3 is to choose landmarks that are close at hand, rather than far away. 4 is to take bearings as quickly as possible. And 5 is to take the bearings of objects that are ahead or astern first, and objects that are abeam last. There are many other sources of position lines apart from the hand-bearing compass. Here, for instance, the two chimneys and Cardinal Buoy appear to be in line with each other. We don't need to mess about with variation or deviation, but can just draw a line through both landmarks. That's called a transit, and it's probably the most accurate and reliable position line of all. Radar is very good at measuring distances. Knowing that the headland is 1.42 miles away, we can draw a circle on the chart with a radius of 1.42 miles and centred on the headland. It's a curved position line rather than a straight one, but the principle is just the same. It can be crossed with a couple more position lines to produce a fix. Even if you haven't got radar, it's sometimes possible to estimate your distance from a lighthouse by noticing when it disappears below the horizon and using dipping distance tables. If nothing else, the echo sounder will often provide a quick check that nothing is grossly wrong with your fix, and it can provide a position line in its own right as you pass a depth contour. As we've just seen, a traditional fix needs at least 2 position lines, just as a GPS fix needs at least 3 satellites. Even if there's only one landmark available, though, all is not lost. A single position line doesn't tell you exactly where you are, only that you're somewhere along it. You can always make a best guess at your position, though, and work up an EP from that. If you had really been here, then the EP shows that you're now here. But you weren't. You were somewhere along this line, so you must now be somewhere along this line. It's parallel to your original position line, but passes through your EP. It's called a transferred position line, and can be used as one of the position lines in a new fix, by crossing it with a new bearing of the same object. At night, the scene changes dramatically and it becomes difficult, if not impossible, to pick out where the land, sea and sky begin and end. Lighthouses go a long way to solving the problem. Unlike street lamps, they aren't intended to replace natural daylight, but are there to highlight and identify important headlands and hazards. To do that, each lighthouse has its own distinctive pattern of flashes. A description of the flash pattern is given on the chart. Here, for instance, it's 4 flashes every 20 seconds, which means this is Portland Bill Lighthouse. Of course, lights are shown from lots of things other than major lighthouses. They all, however, have their own distinctive characteristics of colour, rhythm and period. The simplest of all are fixed lights, showing a continuous, unchanging light. A light which blinks out from time to time is known as an occulting light. The time interval from one blink to the next is called its period. This, for instance, is an occulting light with a period of 5 seconds. The blinks can be arranged in groups, in which case it's called a group occulting light. The abbreviation on the chart is still OC, but the number of blinks in each group is shown in brackets. If the blinks of an occulting light are made longer, so that they become the same length as the intervals of light in between, then we're looking at what is called an isophase light. Of course, if we take this process further, we get to the commonest and largest class of all, in which the short periods of light are separated by longer periods of darkness. This too can be varied, much like the occulting light, by showing the flashes in groups. There are other variations too. You might come across more complicated rhythms in which the flashes are shown in several distinct groups. The flashes can be lengthened to 2 seconds or more. Or they can be speeded up to about 60 flashes per minute. That's about the same as a car's indicators, and it's called quick flashing. A light flashing faster than 80 flashes per minute is described as very quick. And you might even come across a few lights classed as ultra-quick, because they flash more than 160 times a minute. Buoys and beacons are sometimes called the signposts of the sea. They are really more like warning signs, telling us about hazards such as wrecks and shoals rather than giving directions. Around Europe and the UK, you'll come across 2 distinct types, known as lateral and cardinal. Lateral buoys are used to mark the edges of channels. To stay in the channel when entering harbour, keep the red cylindrical or can-shaped buoys on your port side, and the green conical buoys on your starboard side. Of course, when you're coming out of harbour, the buoys are still in the same places, so you need to leave the red buoys to starboard and the greens to port. It's worth bearing in mind too that many buoys are laid for the benefit of ships, and the best place for small craft is just outside the channel that they mark. Many of the smaller creeks and harbours that are of interest to us are marked by piles or beacons like these instead of buoys. The colour code is the same, red to port and green to starboard when entering harbour. Many piles also carry top marks, replicas of the buoys they represent. Lateral buoys are sometimes used in more open water, where the rule is that you leave red buoys to port if you're going clockwise around a continent. Isolated hazards, or for forked and branching channels though, are often more guarded by cardinal marks. They come in a wide range of shapes and sizes, but they're always black and yellow and have top marks consisting of 2 black cones. A north cardinal mark is likely to be found to the north of a hazard, so the safe water is to the north of it. The cones of its top mark point upwards. You can think of them, if you like, as pointing towards the top of the chart. The black bit of the buoy is at the top too, and it has a yellow base. A south cardinal is south of a hazard, with safe water south of it. Its top mark cones point downwards, so you can think of them pointing towards the bottom of the chart. The downward pointing cones are also a reminder that the black bit of the buoy is at the bottom. A west cardinal lies west of a hazard, so you should aim to pass west of it. Some people think its top mark looks like a letter W on its side, while the fact that its cones point towards each other is a reminder that the black bit is in the middle of the buoy. Finally, there's the east cardinal, lying to the east of a hazard, with the best water to the east of it. Its cones are points apart, so you might be able to imagine that they make the shape of a letter E. They certainly suggest that the black bits of the buoy are at the top and bottom. Many cardinal buoys have lights, conforming to what has been called the clock rule. At the 12 o'clock position, the north cardinal flashes groups of 12, except that because there are so many flashes in each group, they merge together, to become continuous quick flashing. At the 3 o'clock position, the east cardinal flashes groups of 3. While at 9 o'clock, the west cardinal flashes groups of 9. The south cardinal at 6 o'clock flashes groups of 6, but to help distinguish it from the west cardinal, it also has a long flash at the end of each group. Most hazards are marked by lateral or cardinal marks, but there are a few others that you're likely to come across. This, for instance, is an isolated danger mark, used to mark small hazards such as wrecks or isolated pinnacles of rock. It's black and red, with 2 black balls as its top mark. If it has a light, it's group flashing 2. This one is a safe water mark, mainly used to mark the beginning of a buoyed channel. It has red and white stripes and a red ball top mark. Safe water marks are usually lit, with either isophase or occulting lights. Finally, there are a host of special buoys, used to mark things such as the centre lines of major channels, the edges of bathing areas, or as race marks. They are invariably yellow, but can be of almost any shape and may or may not have a cross-shaped top mark. So far in this programme, we've been mostly concerned with equipment and techniques for finding your way across open water. Close inshore, and particularly in rivers and harbours, finding your way may be less of a problem, but you're very much more concerned with avoiding the hazards that may be only a few feet away. It calls for a different kind of navigation, known as pilotage. In a well-marked entrance like this, the channel is pretty obvious, so pilotage is a simple matter of steering the boat to pass between the piles. It still pays to keep your wits about you, though, as sometimes the piles are far from obvious. Where the marks are further apart, it calls for more care and a slightly different technique, which we'll call buoy hopping. Here, for instance, there are lots of marks in sight, but they're all a long way off and there's no obvious channel. A look at the chart shows why. In this case, there are several different channels, all with their own marks. The solution is to plan ahead and set out a route from buoy to buoy.
Okay, Ray, do you see the crane 10 degrees on our port bow?
Yeah.
In line with it, there's a green post.
Label the bearing and distance from each buoy to the next on the chart, or make a note of them. Then, as you approach each buoy, it's a relatively simple matter to look in the right direction to find the next buoy. Buoy hopping works well in the right circumstances, but it does have its problems, especially when you're moving quite slowly in a strong tide. Here's why. As you start off from one buoy, heading for the next, the tide pushes you sideways. At first, that doesn't seem to matter. You instinctively alter course to aim for the buoy. A bit later, the tide has pushed you even further sideways, so you alter course again. What isn't always obvious from on board is that although you're always aiming straight for the buoy, you're being pushed further and further off track. The end result is that you could end up on the very sandbank the buoys were intended to help you avoid. The other possibility is that when you eventually arrive at the buoy, you'll be approaching from completely the wrong direction. And when you start looking for the next buoy, it won't be on the starboard bow, as you might expect, but is somewhere behind you. One solution to this problem is to use transits, two objects in line with each other. Here, for instance, we've just left one buoy and are heading for the next. You can see that there's a chimney on the shoreline beyond the buoy. It doesn't matter if the chimney doesn't appear on the chart. The fact that it's staying lined up with the buoy means that we can be sure we're following our original line of sight to the buoy and are not drifting off track. The follow-up to this is that if we can find two landmarks that line up with each other, we really don't need the buoys at all. Here, for instance, the chart shows that our best line of approach is here, and that we'll be on the right line when the War Memorial and the office block are lined up with each other. It's obviously important to make sure that you've found the right marks, but once you have, then staying on track is a simple matter of keeping them lined up with each other. Transits are so useful that many harbours have marks set up specially for the purpose. Transits are incredibly precise. If you're just a few metres off the line, it'll show up, as the two marks appear to drift apart. This can be a bit of a drawback, especially if the channel is busy, or if there isn't really any need for such precision. The approaches to the River Yam in Devon, for instance, are obstructed by rocky ledges on each side. But there's still a wide funnel-shaped area of safe water before we get to the transit that leads into the river itself. A transit would be unnecessarily precise, so the key to this approach is the church, here. If we were anywhere on this line, the church would be on a bearing of 002 degrees. And from anywhere on this line, it would be on a bearing of 043. In other words, so long as the bearing of the church is anywhere between 002 and 043, we know we must be somewhere in the safe sector. In practice, there's no need to be quite this precise. It would be better to give ourselves a safety margin and work on limits of, say, 010 and 035. These pre-planned position lines are called clearing lines. There's no reason why they have to be based on compass bearings. Anything that could be used to provide a position line for a fix can produce a clearing line. Here, for instance, we're using radar to monitor our distance off the shore, to keep away from shallows close by. Another interesting variation on the idea of clearing lines is this thing. It's called a sectored light. This one is designed to shine a white light down the centre of the entrance channel, with a red light showing if you drift too far to port, and a green light showing if you drift to starboard. Here's how it would look as we motor diagonally past the mouth of the river. From here, we see it as an isophase green light. We are to starboard of the correct line. As we come in line with the channel, it becomes a white light, and then a red light as we move across to the port side. To stay in the channel, all we have to do is to make sure we're looking at the correct light, and then stay in the white sector. The whole point of pilotage is that it's quick but accurate and can be carried on without spending a lot of time on chart work. It depends on planning. The object is entirely defeated if you have to keep searching for information as you go along. There are plenty of books and publications to help. Almost certainly the first task will be to work out, at least roughly, the height of tide at the time you expect to arrive. Now you can take an intelligent look at a large-scale chart. Knowing the height of tide will tell you whether you're dealing with a narrow channel between mudbanks or a wide expanse of water. You need to look for things that will limit your freedom of choice, such as sandbars or locks, and for the hazards you need to avoid, and the navigation aids that will help you to avoid them. From all this, you should be able to come up with a route using a combination of the 4 main pilotage techniques we've just covered. The culmination of all this is the plan written down on the chart or in a notebook. At the very least, it should include the direction and distance you need to travel at each stage, and the direction you need to look to find the next landmark.
Okay, quite a long way beyond. Over on our port side, do you see that there's a white cliff in front of us?
Yep.
The right-hand edge of that white cliff, there's another yellow and black post.
Yeah, I've got it.
Okay. For the moment, I'd like you to aim for that. About 45 degrees off our port bow at the moment. There's a green post. Do you see where the edge of that mudbank is coming down?
Yeah.
In a moment.
We've covered a lot of ground in this programme, from the basics of reading a chart and tide tables, through various ways of working out where you are and where you're going, to the techniques you can use to find your way safely into harbour once you've arrived. Just one last thing, though. Do be aware that navigation isn't all about books and paperwork, or about pressing buttons and staring at screens. Nor is it about knowing exactly where you are all the time. It's about knowing enough about where you are and where you're going to be able to relax and enjoy your boat. An Amberley Marine production.